Test. Hello guys. I think in the next period of time we're going to be focusing on parallel systems and parallel programming and trying to get better at that. So let's make a folder called parallel systems. Let's go in here and kind of talk about what I mean. So there are 4 different kinds of parallel programming that you can do, at least as far as I'm aware. There's like SIMD/vector instructions. So it basically means that the CPU can do things like x plus y, but actually in modern CPUs it can do like 4 or more in parallel at the same time without any extra cost or anything. So single SIMD stands for single instruction multiple data, so it can do a plus, that's the single instruction, on multiple data, so that's different x's. Yeah, so that's one way. Another way is like threading. So a single CPU core can sometimes run multiple processes. They don't necessarily always run in parallel, but they run concurrently. So in parallel means they run at the same time. Concurrently means that the process is kind of switching back and forth. But anyway, it's a form of parallelism. You can think of it that way. Then there is like multiple processes. So that could be like multiple CPU cores. It could be multiple computers. So more general, right? And the final one is like dedicated hardware acceleration, we could call it. And that covers like GPUs or what we'll do, probably general purpose GPU. Then there's also stuff like tensor processing units. I think Google has made one of these and things like that. So there's many different ways, and I kind of am familiar with how to program for all of these things, some more than others. But what I'm really interested in is like exploring what are some parallel systems, like what are some systems that actually require or benefit a lot from doing parallel programming. And in the process of that exploration, of course, we'll learn about all of these things. Now, today, I just want to look at OpenCL, Open Compute Language, which is a way to do parallel programming, if I'm not totally mistaken. And it kind of works both with GPUs and with processors and maybe even with threading. Don't think it works with vector instructions, but we'll find out. So today it's just about setting it up. And the way we're going to do that is by Googling it. So let's Google OpenCL. Open Computing Language is a low-level API for heterogeneous computing that runs on CUDA-powered GPUs. Okay, so this is NVIDIA saying that. Let's go to Wikipedia and go here. So this is kronos.org/OpenCL, so that's this one. The last one was released in 2020. So why don't we why isn't there like getting started? I mean, I really don't like Kronos Group in principle for this Vulkan API. If you ever tried that, you'll know it's completely crazy. Okay, getting started on Linux. Let's try that. So OpenCL is included in all main distributions. Okay, it means we probably don't have to download it. In this guide, we choose Ubuntu. We're going to use the following tools: command line, great, C, C++ compiler. Let me do this. So we do have that. We have to have GCC. And depending on which way one extends the bare minimum, CMake, probably not gonna do that. Okay, do we have make? We do have make, we have CMake. We also have CMake. So in case we need it, we have it. We have Git. We're not going to be using that. We're not going to be using that. Okay, in this tool, we'll be using the latest Ubuntu 20. So it's a little bit old. I have 22. First, update your system. I'm not really going to be doing this because I have all those tools. But why don't we try to run this thing? So build native OpenCL applications, one of minimum leads, C++, OpenCL headers, installable client driver. The best way to obtain these files is using the package manager. Cutting edge versions may be obtained using C++ package managers. We're not going to be doing that. Okay, I think we're just going to do this. And let's run that. Okay, so that seems to have run. And now we can, compiling on the command line, compilers native to Nixos flavors, work out of the box, then navigate to the folder where you wish to build your application. Okay, so this is like a minimum kind of thing. So let's see, we don't have anything really here. So let's make a new folder that we call OpenCL start. And we'll go in there and we'll make main.c and we'll paste this stuff. So it's a little bit too zoomed in. So we got stdio, and then we have the OpenCL computing language headers. We have some success type here, number of platforms. So we can get platform IDs, whatever that means. And let's try to run it. I like to make a, well, let's make it over here. I like to make like a run script. And it's just gonna be main.c, and then we can also run it. And we should probably do like set e. And then we can go ahead and say, try to run that. Okay. CL target OpenCL version not defined. So it seems like, why does it say apt? But anyway, it seems like you need to, yeah, have some kind of flags here. So what do we need? They are adding some warnings. I don't like that. And then we can define this to be version 300. I think it's what it said, defaulting to 300. I like that. And then we have to link to OpenCL. So let's try to run that one. And it says one platform found. Great. So there we go. We define which version we want, and then we link to the library. All right. That's amazing. Now, how do we figure out whatever C compiler? How do we figure out now what kind of functions we have to play with? Because it's not very interesting. It's not very interesting to just know how many platforms there are, whatever that even means. I wonder if it says that platforms. It doesn't even define, so what doesn't even define what an OpenCL platform is. That's a little bit to bright. Let's change that. It's a good trick if you want dark mode on a web page that doesn't have it. You just get the HTML element and you put filter invert on that. Okay, I'm trying to learn OpenCL. However, I want to learn if I have. Yeah, what is a platform? Platform refers to vendors, or rather OpenCL runtime drivers. With one Intel CPU, two NVIDIA GPUs, one AMD GPU, will have 3 platforms. Okay. So what? Just let me check something here. I kind of thought I would have 2, but I guess we will try to figure it out. Let's go back here. Okay. We did getting started. So we're inside something called OpenCL guide. What is OpenCL? How does it work? How does it compare? Is there like a freaking reference manual? Get platform IDs, get platform info. This is pretty horrible, but okay, so we have platform IDs, so why don't we get platform info? So CL int info code, CL get platform info. We're just gonna turn Copilot off right now. So we need a platform ID. We know there is okay, so actually we should kind of like do this again, and then we need to, so here the second argument you can get the platform IDs. So we should say CL platform ID and we call IDs, and we can like allocate number of platforms times size of CL platform ID. That should work. And then instead of null, we can put the IDs, and then it should be like put into that that pointer. So now we can go ahead and say retrieve IDs and fail to retrieve IDs. Before we go further, let's try to run that. So it failed to retrieve IDs for some reason. And why is that? Number of entries. So maybe here we have to do this. Tell it how many spots there are. Okay, so we retrieve the IDs. And now we can get the platform info for the first one. Is that how you do it? So the first one is the ID. Then there is some kind of parameter name, and I see some parameter name. Parameter names here. CL platform X, where X may be extension version, host time, resolution. Let's try name, and let's try CL platform name. And parameter value size. What if we put 0 and null and null? And well, we have to put the thing in there, right? But let's just try to see if this even like compiles. Retrieved info, failed to retrieve info. So we did manage to call this, but we don't know what happened. Parameter value size, parameter value. So let's say size t, value size, and I don't know. Is it like in bytes or something? Let's do this. So then let's do parameter value, and we can just gonna do something to get the indentation. So let's allocate all of this, and like just for some bytes. And the last one is parameter value size return. So we also need to know like what is the actual size, the final size. So param value size. Let's go to new line and say parameter value and parameter value size final. I think this is how you're supposed to use it. And got size. And then we can say parameter value size final. Let's see. Okay, so got size 12, but do that. Okay, so got size 12. Let's put this one down here. I kind of like that a little bit better. Give it a bit more space, and there we go. Okay, so we can retrieve that. And should we try to just print, like pretend it's a string? Info is, we pretend it's a string, and then we're gonna say parameter value. NVIDIA CUDA. Okay, so it captured my GPU, but not my CPU, which is Intel, and according to Stack Overflow, that should also work. But I'm not gonna really worry about that. It's enough for now that we have the GPU. And did I already click that one? Yeah. Source. Okay. There must be a better way than this, but it got us part of the way. I remember it as being somewhat simpler. Like, can I just get a small example? OpenCL 3. No, that's not the one. Programming model. I don't care. Just give me, what do they have in images? Just some images. C++. How to implement kernels for complex number arithmetic. Not interested in that. Additional resources. CMake build system. How does it work? I don't care how it works. Why is OpenCL guide and there's almost no code? Like who made this? I think we're almost about to give up. OpenCL resource manager. Let's try that one. So what are we looking for here? Resources, homepage, registry. I guess we can try this one again, and now we're back here. Maybe there is something. Standards, don't care about that. Reference guides, maybe. Books. I mean, do I really have to buy a book to add this some reference guides? I can buy one. Great. How about you just show me some code? Okay, so now I'm giving up. Now I'm gonna go get a Google OpenCL tutorial. And how about this one? This is from some kind of university without dark mode. Okay, tutorial covers the following aspects of OpenCL programming. Check for this, we did that. Memory allocation on the device, data transfer to the device, retrieve from the device, compile C programs that launch OpenCL. Perfect. So references, let me close all this crap and this crap as well. And here we go. Okay. Maybe we just continue with this because it's a little bit nicer. Connecting to some cluster, we can't really do that. CL info is a thing. Okay. Apparently not. Apparently not on my device. Okay, it's not available on this cluster, so maybe it's not generally available. Platform model. Model consists of a host connected to one or more devices. An OpenCL device is divided into one or more compute units, which are further divided into one or more processing elements. Okay, so the GPU, we think of it as several compute units, which each has many processing units. Computation and device occurred within the processing element. Okay. And there's like two things: host code, so CPU code, and code and device code that runs on GPU. And that's it. So we communicate through the global memory of the device. And there's also a memory hierarchy, but we won't think about that right now. Using the C++ bindings of OpenCL. Okay. That's not so nice that they use C++, because I don't want to do that. CL buffer. Yeah, and then because the C++ you have no idea of what is happening, because it's all inside some constructor. So why is it in Spanish? Let's go here. And I'm going to copy this code. And then we are gonna go ahead and make what should we call it? Let's call it reference. It's kind of like a reference. So you have a reference here, and this is also unfortunately using C++. Okay, but let's take a look at this kernel code. So we go back here. So we have this kernel code, and it's not a string, but it is an array of characters. So what do we have? We have void. It doesn't return anything. It's a kernel code. We call it, the name of the function is simple add. It takes an array of integers, an array of integers, and an array of integers. But this one is not constant, so probably this is the result. And we do a plus b. So let's write kernel code for a plus b for each element the arrays. Okay, so inside the code we have C and then get global ID, and then it's A plus B. So this global ID is probably referring to this processing element. So we will like send this code to run over many different elements, and then each one will have a separate ID, and that ID is kind of tasked to handle one part of the array. Right. So that's our kernel code. Can we make any sense of this? So they're making some kind of some sources. There's a context, and we have the device name, program build. We also have to build it. So I think they got the platforms, right? And they got the default platform. Okay, so this one probably doesn't have to be so large. So let's make it 10. And then we can say using platform, let's comment out these things. Here we're just going to return 0, return -1, and that's fine. And here we're also going to just return -1. Okay, so again, if we run this, now it says failed to retrieve info. Maybe this was too short. Let's make it a little bit bigger. Okay, yeah, so this is like the number of characters, which was more than 10. So we use CUDA, and then we need to get a device. So maybe I do want to go back here and say, this one, was it? No. Programming, no. How does it work? No, this one. Yeah, I think it was this one. So then we can get device IDs, which is what they do there, I think. Maybe, is it possible to just get the header? Like, where would that be? Like here, and then, no. I'm gonna try to find that. I'm just running this find command, just searching through everything I have. So what was the header called? On small c, small l dot h. Okay, I think I found it. So it should be here, include EL, and we should have a bunch of stuff. So let's look at this one. So this might be a bit easier to look at than that weird image they have, especially because we can like copy things. So there's like something called device. Yeah, so get device IDs is what we want now. Let's put that here. And what is the platform? Well, we already decided that, I think. So let's go ahead here and say platform ID. ID is just the first one. Okay. They call it platform. I'm gonna call it platform. So we have the platform, then the device type. So we don't have that. We don't have that. But it can be, can we see that? Can we see like what is allowed here? We can say device type all. So like we don't really care, I guess. A number of entries, get device IDs. What does that mean? Who knows? Let's put one. And then we need the device ID, devices, and here maybe, so it should be a uint, and we can say device capacity is 1, and then we're gonna allocate that. Devices, and then we need to know how many devices we actually got out. I do that like this, and what's that? We don't know. This thing, let's indent it, and let's get the info code out, and then we can do this check again. And then we can say found devices, number of devices, failed to retrieve device ID. Let's try that just to see. Okay, we found one device, it worked. And let's also do this with ID and devices 0. Okay, it doesn't like that because format DXP argument, but argument 3 has type CL device ID. So we have no idea how to format that, I guess. So a device ID is actually a pointer to this struct, which is absolutely crazy, and we don't know what that is. Okay, so whatever, we have some ID, and here we can just put some -1. That's okay. So then we have the device ID, then there's device info we can get. So again, info code will be the device ID. So we have device 0. Maybe we go ahead and just like do this. Let me say device info. So what is device info? As parameter name, it's a bunch of stuff. We don't really care about that so much. How does it work? Wait, it was here. It had something interesting. Programming model, processing elements. Okay, so maybe we want to find that, like how many processing elements are there? Which doesn't seem to be a thing. But we can say max workgroup size, for example. Let's try that one. So max workgroup size. And then we have to kind of like get that out. So param value size. Do I already have that? At this point, we have so many like temporary allocations that we should kind of like do this. Define the temp size can be 124, and then we can say temp size, and what's the param value? Yeah, let's just do that. So it's gonna be some characters in an array. Oh, isn't that, that's not how you do it. Kind of forgot how to do C. Temp size, and like that should be it. And param value, and then we need the actual size. So actual size and actual size. All right, let's just indent it. And now we need this printing again. So if the info code is not a success, then we're going to say max workgroup size is this thing. And here we're going to say filter device info. So let's see if that runs. That is not a thing you can do. So what is this device info? It's a uint, but here we have them. So CL device. Yeah, so we have to say CL device max size. And we, fortunately, what should we call it? Let's call it info value. And now I need a little bit of a debug. So size. Eight. Okay. Should we print it as just a character and then a space info value I, and then we can just print a new line here. And let's put some quotes around it. So what is that actually? If we do this, weird. So I don't know what that means. What if we try to do this? That's not it. And this, of course, doesn't work. It's just going to give 0, which is not true. So does it say anything? No, it doesn't. And it's also annoying that it's like a void. So you don't know what kind of thing it's supposed to return. Get device info. And this thing doesn't tell us anything, right? No, so maybe it's time to look at our reference. Device name. So can we do that? So CL device name. And yeah, so that works. That's fine. Don't need the actual size. We don't need a new line. So now it just gives us the full name, which is I don't really care about. This is like max workgroup size. This is really something I would like to see, but it doesn't work. What do they do anything else in the reference? So do they have any other infos they get? They don't. They get a platform name. That's something else. Okay. Then they create a context. And then they set up some sources, and then they build a program. Okay, and then there's some buffers and some queues and stuff. Why can't we just do simple C example? And no C++. Add numbers, this is the one we want. And it's with C. So this is a better reference, I think. Create device. They get platform ID. Then they get the device ID. And then they just return that device ID. And what does the main look like? They create the device, they create a context, they build a program, create some buffers. Okay, let's try to build something using this. So this idea. So what is the type of this? It's CL device ID, and we're going to say create device. And how did we do that? So first we need a platform ID. So let's say like this, CL platform ID, and let's just do one. Right, so we have one, and we have, can write it there, a number of platforms. That's all right. To get that, and I'm gonna use my preferred casing like that. Okay, so we got the platform and we got an error, and then we're gonna say if error is not success, then maybe we just, is exit a thing? I think it's a thing. We're just gonna exit, we're gonna say could not get ID, and that's it. We're not gonna think too much about error handling. Okay, so we have the platform ID, now we need the device ID. So we don't really want info, maybe we'll, like, it's kind of fun to have some info stuff. But anyway, so the error code is now going to be this. We get the, so we can call platform device capacity. So CL device ID, I call it device, and there's just one, and this is that. And then the actual number of devices, which, what was that? That was a uint. So we have that. We do the error handling. Could not get device ID. And then finally, I guess we return that. And let me do this and say CL device ID device create device. And did a bit of an oopsie and an oopsie. And what else? 35 looks okay to me. So I'm looking at the wrong thing. So we have to say, we have to kind of use it. So we use it in a fake way, and that works. Okay, so we can get the device. And what was the next thing? Why don't we copy this? This is a much better reference. And delete that and put it in here. Okay, it copied it in a really fucked up way, so we have to do this. Okay. So the first thing we did was create a device, then we can create a context. And a context, not sure what it is, but it's apparently using the device. So let's say it's probably gonna be context ID, because that's how they like to do it. Right, context null. We can also check this one out. Well, let's not do it that way. So let's do it this way. CL create context. It takes a bunch of crap like properties, number of devices. But let's copy this over just so we know what we're dealing with. So properties, we set it to null. Don't care about that. Actually, what did it return? It returns a CL context, so not a context ID, but just a context, which should also be what we see here. CL context, yes. Okay. So what do we do? Properties. We don't know what that is, so we're going to set it to null. Number of devices. We only have one device. Device IDs. Okay, we do have that. That's just device. Some kind of callback. That one. Oh. That one. Callback. Let's Get rid of that. That's also null. User data. We don't know what that is. We're gonna put it to null. Error code. So maybe we do want to get an error. So error. Say error. It's very nice that sometimes it's the return value and sometimes it's like an out argument like that. Okay, so if error is not equal to success, and if fail to create context and exit, return nice one. Let's try to run that, and it doesn't work. So we say void context. I'm going to turn off warn all, I think. Maybe. Okay, so now we need to build a program, and it has here program file. But how do you even build a program? How do you build a program? Let's first check out this thing. Create program with source. Create program with binary. Create program with built-in kernels. IL, retain program, release program, build program. Compile program. Link program. Lots of programs. Okay, so create program with source. I think we should try that. It returns a CL program, and it has a context. We already got that. It has a count, which I guess is the number of programs. We only have this one. Then it has kernel code pointed to that, and lengths. How are we gonna do that? How are we gonna get the length? So just for now we do this, and let's say size t, code length, string length of kernel code, and this can just be the pointer to that code length because there's only one. And then we need the return, so like that. And let's do this. And if we get an error, we're gonna say fail to create program. Okay. Let's run it. It worked. So we created a program with source. So what does that mean? Because there's also like build program. So it takes a program, chain program. Let's try to build it. So try to build it, and that returns some kind of integer. Maybe it's just the error. That would make sense. It takes the program. It takes the number of devices. There is one. It takes device IDs. We only have one. Options. Let's try null. This one, let's try null. And this one, let's try null. Good. And we want to check this again. Fail to build program. Too few arguments, so something went wrong. Options, null, device, yes. Null device, yes. Options is null. This callback is null is not a function or function pointer. But didn't we do that before? Didn't we do it in create context? That was also a callback. This is the problem. So look at the highlighting. Okay. We build a program. Let's see if that's actually what they're doing in the reference. So they have build program, which opens the file, whatever. We don't care about that. Create program with source. That's what we did. Free program buffer. So you can kind of free the source now, but we don't do that. Then we build the program. It's kind of interesting that they don't give the device. We don't have to do that. If it fails, you can get a bunch of information. We don't want to do that right now. Okay, Intel recommends workgroup sizes of that. Really Fermi. Yeah, so now it would be nice to be able to actually get some information. What's that? Just that this code. Maybe we can turn this into a function. Let's put it here and let's say print device info, and it should take some kind of identifier. So CL device max compute units, max workgroup size. But anyway, what is this? What is this CL device info? What is the type? It's just, okay. So CL device info ID, and then we're going to turn this into a nice convenient function. Here we go. Let's also have a something here that we can put things into. So get away from me, and this one should be the info ID, temp size, info value. Here we can just put it into temp, and let's do this. If the info code is success, then we print the info, and that is from temp. We're gonna have to go ahead and say temp, and here we just print that. So let's try that. Get print device info, and I want to try some things. It should really be a macro, because I need to do some stuff. It's just going to be like this for now. So we're going to go ahead and say print like, let's try some of these. Okay, then we're going to say delete that, print if this is the info, delete print device info. What it's gonna be? It's gonna be this stuff that we then put here, and that, and then we go here, and that's a macro. So we can just run that a couple times. Okay, get rid of that. And let's see if that runs. It did not run. 20. Okay, it's because it's not this one, it's just info code. And Device. Okay, we need to, of course, provide the device. Device ID, device. Makes a lot of sense. Let's do it like this. Device CL. Okay. And now maybe we don't do this, we just print whatever it is, and then let me say give space here. Okay, we have something now that, like, this is, do we have to do like ASCII to integer? But that it's not really ASCII, right? So didn't work. Okay. This is very annoying. Is OpenCL device info. How does that work? Like, let's see if he has max compute units. So get device info, max compute units, whatever. So go away, GitHub. So max compute units. So he's kind of putting it into an integer. And that's the problem. That is our problem. Because you have to know that you want an integer. So info. So this has to be size of info. This has to be info. This one we don't really care about. What does he do? He does give it null, so we can do that. Null. And it's not that, it's actually just a number. Okay, max compute units 24, max work item dimension 3. What is so group size is probably something else. Of course, it's something else. So can we just say size t? Yeah, we could say that max work group size is 1024. So now we need work item sizes. So that's a bunch of things. So it's very annoying to use because it's not the same kind of thing. But maybe we can make that easier for ourselves. So max compute units. This script is kind of nice actually. I'm going to let's call it description. I am going to save that here. Okay. Let's put this a little bit higher right after we create the device. So we have that. Next, we have built the program. Now we should probably try to run it. Let's check out our reference again. So far so good. We built it and then he returns it. So now we can go ahead and see what he does with the program. Global size. Input buffer. Okay, so we are kind of here. Now we are making a buffer and he's using some kind of Fortran style CL memory. It's so weird that they like to define their own weird types. But what is it actually? It is also some kind of pointer to something you're not allowed to know what it is. Okay, but we can create a buffer. We use a context. It's read only, or we can copy from the host. That's how I read this. We can copy from the host. Array size is not something we have. We can define that. Array size, it's some float, it wants some data, and it wants to output an error. So let's set up the data. Let's set up the data. What is the data? What is the stuff even doing? This was the add numbers example. So let's just put the data up here. So that's the data, there's an error, and then let's check the error. If error is not success, then fail to create input buffer. Return -1. So this is putting some data on the device, I think. Do we have to remove it? We probably have to remove it again. So why don't we just do that right now? Why don't we just do that right now? So we don't forget. And it worked because it didn't fail. That's how you know. So let's actually print that. Done. Everything good. Can write it again. Okay, so we create that. We can also create something that holds the result, I suppose. So this one is read and write, and again we have this copy host thing. Okay, so we have maximum workgroup size is that. So we know already that the number of groups is some type CL integer, number of groups. Why don't we try to put it to the maximum? Well, it should not, then this should probably also be that number. So we have that many numbers. Could also just initialize the data. Now we're at it. Put some stuff in there like this. I think we can probably get rid of that now. Let's just make a temporary file so we don't lose it. Okay, but we put some stuff into the data. We set some stuff up. And we create the input buffer, the result buffer. I think. Let's see, let's look at the reference again, and we should probably also let's put this in the description because that's also extremely helpful. Anyway, let's, okay, here we are. Create kernel, create command queue. So what is it actually doing just for fun? It's doing some very complicated stuff. So we get the data, there's some local result, there's a group result. This is a little, and it's kind of like summing, and there's a barrier. It's not really the simplest example. Sum array. So we are going to try to modify it a little bit. Let's call them data 1 and data 2 and result. And then we want input buffer 2, 1, result buffer. And this one will be input buffer 1, 1. And instead of data, it should be instead of data, it should be data1. Copy that. Actually, then we have to do that twice as well. Sorry. Okay, and this is now result buffer. It's giving me some warnings now. Ah, and we need to release those. Input buffer 1, 2, and result buffer. And what is this sum? Right, and then when we initialize it, we also have to do some stuff. So just do that, because did it even compile before? Like, how's this possible? Okay, so there we have that. So we create some buffers, and now we have to create some kind of queue, which is always nice, and the queue has to be freed, I think. And that has a type of CL command queue. And create queue. Okay, it takes a context, device, and error. And we can do that again. So if failed to create a queue, then we need to create a kernel. And I like to say if it's not a success code, then print F and return -1. Now, what is this kernel function? It's whatever the name is, I think. So for us, it's simple add. And we have to free the program, free the context as well, and release the kernel. So let's do that. And let's run it. So did not compile, and this is kernel. Okay, so we're able to do all that, but we haven't run anything yet. So that's perfect. That's perfect. Perfect. Kernel arguments. So we have to set some arguments. Take the kernel, the first argument, and now we have to specialize it to our stuff, which is this one. So the first argument is input buffer 1. Second argument is the same, except it's 2. And finally, the third argument is the result buffer. And if that is not equal to, then we couldn't create the kernel argument. So let's try that, and it works. All right, so we create the arguments, and then we have to kind of tell it to run, and then we read the result. So we say in queue this kernel. Let's see what that is. So CL in queue ND range. That is a bunch of stuff. Okay, error equals this. We need the Q. So we call that just Q. We need the kernel, that we call just kernel. We need the work dimension. What is work dimension? Do we output that? Work dimension. Don't. You know what? Let's get this script. So it's going to output a bunch of information. Let's get it here, and we'll call it. We will call it. We will call it info. So we have info, and now we can try to run that. So then we have to kind of modify this run script. So this one we're gonna this, and then we should say run. Okay, that doesn't run, but we can say we want to run the info, and it gives us a bunch of stuff. And also a bunch of errors. Okay, one is available, and then we have some. Where was the work dimension? I cannot find it. Let's try to grab for it. Work item dimension. All right, work dimension. What if we put one? Okay, there's only one dimension. Global work offset. That is null. We can put it to null. Global work size. Does that have something like work size? No. Size. No. So what did we call it? Or what is it in the reference? Global size, it was like a very small number. So why don't we just try to say 1024, and this is 1, the local size, but these need to be global work size. Is that local work size is 1. Let's get Copilot off here as well. All right, so this one like that. Number of events in waitlist. So you can wait for things, I suppose. Wait, has to be. That was the wrong one. This one has to be 0. Pointer is null. And what is the event they're waiting for or something? I don't know. Okay. If it's not success, then we couldn't enqueue it. And then we read buff. Enqueue read buff. So again, we need a queue. We need a queue. We need somewhere to put it, so I think that's going to be the result buffer. Is it a blocking read? I saw that he used CL true. Offset, we want to put it in the mid, in the beginning. Size of the result buffer. Size of sum. What is sum? What is sum? Yeah, so that is actually going to be array size and pointer to somewhere. So this is actually reading from the GPU to the CPU. So where do we want to read it to? It's just called result. Here we can say size of result. It's probably pretty good. Number of events 0. Event pointer thingy. And that should do it. Let's try to run that. And this is a scary moment because I think it's actually computing on the GPU now. So that worked. Now, let's see if it actually worked. So we have initialized these guys with some stuff. The result is just 0. And the code is supposed to just add them together. So what we can do is we can say for I less than array size plus plus if data1 I plus data2 I is not equal to result I, then we're gonna print something went wrong. And we can break. We don't need to run through everything. And let's maybe do this. Something went wrong. Okay. Let's print what the values are. So data1 I equals okay. So that's very interesting. And what's the I? Actually, we should get that as well. We should get that as well. So the first one is wrong, and the first one is correct, but that's because it's 0, and the second one is infinite. What if we let's try this? Then basically everything is wrong. So that's great. That is great. So, okay, so of course what went wrong is we have told it it's integers here, but actually it's floats. Okay, so that worked. And I think that's going to do it for this video. It was a bit difficult to set up, and we definitely want to make a much nicer interface. basically I want to say, here is the code, the kernel code. Here are my inputs, and run that. But we need all these like intermediate variables, so I think we're gonna kind of hide them behind something. Yeah, okay. All right, that's gonna do it for this video. We managed to run something on the GPU. Amazing, amazing. So I will see you in the next video, where hopefully we'll do something a little bit more interesting. And until then, bye bye.